I don't do a lot of product reviews on my YouTube channel, but this is an instance where I thought I would do a short one. As some other viewers of my channel know, I have a sub-series regarding my home electronics lab, and I have a Heathkit model 2240, I believe that's the number, digital LC bridge for measuring capacitance and inductance. And I've also done a separate feature on that piece of equipment since it was not covered elsewhere on YouTube. I've recently acquired some other vintage Heathkit LC or LCR testers that I'm going to be restoring, and I realized I don't really have a factory produced LCR meter to check anything against. So I decided to do some research and decide what was affordable and still looked pretty reasonable. And I selected this Extech brand model LCR200 passive component LCR meter. So this can measure inductance, capacitance, and pure resistance, and various other features and parameters relating to the reactance and resistance of those components. Now, if anybody's looked into LCR bridges or testers, you'll realize that they're usually quite expensive, laboratory grade pieces of equipment. Easily can cost over $1,000, sometimes $2,000 or $3,000 without problem. It can go a lot higher than that, really. And when it comes down to the handheld units, they're usually several $100s. I didn't want to spend that much, and I also didn't want to get one of the nameless Chinese products that's out there, simply because there's usually no support for them. And I've seen a few reviews of some of those, and for the price that was being asked and the likely lack of support, I didn't want to go that way. And this Extech LCR200 actually comes in a bit less expensive than those other ones. Now this replaces an older Extech unit whose number I can't remember off the top of my head. It's a 6-digit number. It's their only other LCR product in a handheld unit. That's a bit older. Dave Jones from the EEV blog did a dissection of that one. Now this is the LCR200, completely different model naming scheme, and it's supposed to be a replacement or an upgrade version of that other model. So what I'm going to do here is just a quick introduction to the unit. I'm not really going to try to review every last nuance of its operation. It's going to be more like first impressions. So anyway, I bought mine on Amazon, and here's the price. They're not the only ones who sell it. That does seem to be a typical price for the unit. Now here's the box it comes in, typical of cheaper equipment. It lists some basic characteristics, measures inductance, capacitance, and resistance with secondary parameter Q for quality, D for dissipation, R for resistance, theta for phase, and the ESR or equivalent series resistance of the component. It has auto selections of range. It has 5 different test frequencies, 100 Hertz, 120 Hertz, 1 kilohertz, 10 kilohertz, and 100 kilohertz. And it has some features to allow sorting of components and rejecting components if they're out of range, that type of thing. It only has 2 accessories which do not come with the basic meter. One is the LCR203 SMD tweezer. It's just a set of test leads you can plug in to the front of the meter, and it allows you to clip onto some surface mount type devices. And there's also a little module which plugs into the front of the meter and allows direct insertion of surface mount components. So with that, let's go look at the actual meter. So here's the meter. It's a fairly good size, a bit larger than your average handheld multimeter. Pretty big LCD display, some soft touch sort of rubber buttons on it. They're pretty typical. It has a set of connectors right there which look like slots, and those have these bent sheet metal connectors that look like Kelvin connectors, but I don't believe they are actually Kelvin connectors. And all a Kelvin connector is, and I can use this illustration here, or this to illustrate it a little better. This is my Heathkit 2240 digital LC bridge. It's my mainstay capacitance and inductance measuring device in my lab. Been very reliable for many years. It stays in calibration pretty well. Anyway, the Kelvin connector is this right on the front here. And for both the plus and the minus terminals, you actually have two plates for each of these slots. One plate on top of the other like a sandwich, and then they're bent a little bit on the front end so that you can slide in a component in between the plates. I'm going to use a capacitor here as a demonstration. So I've just slid that in there, and for each lead there's a plate on top and a plate on the bottom, and they just pinch the leads, and when you pull the component out, the plates for each side come together and they kind of short out. The reason for the Kelvin connector and the identifying characteristic isn't that it has plates. It could be some other type of connection, but the idea is that there's two contacts per lead of the device under test, and one of them will be the signal that's being injected into the component or used to drive the component for testing, and the other terminal on the same lead will be the electrical connection that's measuring the component so that it can reject any capacitive or inductance or resistance effects or characteristics of the leads or the components. That was poorly phrased, but the idea is that you won't skew your reading by inductive or capacitive or resistance characteristics between the front of the meter and the actual component. So that's a pretty important thing for getting the best results. Now, these slots on the front of the Extech look like Kelvin connectors, but based on Dave Jones' teardown of the older model, that one did not have Kelvin connectors, even though they look like Kelvin connectors. I very much doubt this one does either, and that's partially because they just have these banana jacks as standbys if you can't use these the primary integral connectors. And the fact that there's a simple banana connector for each of those terminals, the plus and the minus and the guard, suggests that there's really only one contact for this and one contact for this, and that same contact is electrically connected to the banana connectors here. So I don't really think there's a drive and a sense pair of contacts for each of these. That may not make a big difference, but I would have liked to have seen Kelvin connectors on there. Okay, so what else do we have? It's possible to drive this with a external DC power supply. It requires 9 volts regulated at 1 amp, positive center. It doesn't indicate here or in the manual what the barrel connector size is, and Extech does not have a part that you can buy, so you'd have to provide your own generic power supply if you wanted to do it that way. On the other side is what appears to be a 1/8 inch phone jack, or maybe it's a stereo phone jack. tip ring sleeve type of thing. It's listed here as data output. In the manual it says it's an RS-232 output, and the manual also says that it's not actually implemented. So it looks like they made provision for it but then didn't actually do anything with it. That's assuming the manual is correct, but there's no information or software that I could find to use this with, so I sort of doubt that it has it, at least at the time I'm doing this review. The back of the unit has a typical handheld meter type of kickstand, and under this cover here is a area for a 9-volt battery. The meter does come with a 9-volt battery, but it just takes your normal 9-volt alkaline battery if you want to provide your own. These 2 screws that hold the battery compartment closed, one of them was missing on mine. I've contacted Extech about getting a replacement screw. Don't know if they'll provide one or not. But at least they're into brass inserts instead of just being threaded into the plastic. And that's a mark of a slightly better physical build. There's also this thing here which looks like it should slide off, but it appears to be physically molded on there. I tried to get it off and I couldn't see that it came off. I think it's just, I don't know if it's decoration or what. So let's go over the buttons here. This is your power button. This is your backlight button. It is a backlit LCD. There's a self-test sequence this goes through, and you can start that by pushing the cal button. As I mentioned before, there are 5 test frequencies, starting with 100 Hertz and going up to 100 kilohertz. And depending on the type of component and the size of component and some other factors that you would possibly know about, you might choose to test your component at different frequencies. Some lesser meters only have 1 frequency, or 1 or 2. It's to its credit that it has 5 different frequencies, and it defaults to 1 kilohertz for everything. And if you decide that's too low or too high, you can push the frequency button and cycle through all 5 frequencies. If you want to hold the display, maybe even after you've removed a component from being tested, you can push the hold button. Pushing it again releases the hold. The meter usually auto-detects what type of component you put in, but under certain circumstances or with certain types or conditions of component, it may guess incorrectly. So if it doesn't auto-detect correctly, and it'll say on the screen whether it's testing for an inductor, a capacitor, or a resistor, if it's guessed wrong, you can push this button to force it into the right mode. These 3 buttons here have to do with setting up the meter to sort components. I'm not going to get into the details of that, but it does have that feature. Now these 5 buttons here, the middle one's the power, as already mentioned. The other 4 surrounding it are navigation buttons, up, down, left, and right. And those are to navigate through the display to do certain kinds of setup. For example, you can use this button to set up a component inspection type of feature where it'll reject components that are outside of a certain tolerance range. Say you're trying to dial in parts that are really close to a desired value, and you wish to reject components which are further away from the ideal value. This meter has that feature, and you can call it in and set up your percentage tolerance and so on. The meter is able to work with a component by regarding it as a series combination of primary and secondary characteristics, or a parallel combination of primary and secondary characteristics. For example, if your primary characteristic is capacitance, and then your secondary characteristic is the ESR, or equivalent series resistance, you'd probably want to make sure that it's in the serial mode so that it's looking at it as a capacitance in series with a resistance. but you don't necessarily have to do it that way, and sometimes there's more complicated scenarios you get yourself into. You want to force the meter to regard the component's primary characteristic and its parasitic characteristics as a series or a parallel combination, and that's what that's for. The primary characteristic is the LC or the R as you've selected here, or it's auto-selected. Then there's the secondary characteristic, which is displayed simultaneously, and this button here is what lets you pick that. For example, the dissipation, the quality, the theta, the ESR, that type of thing. You can select with that. So really this is for selecting the primary display, this is for selecting the secondary display. And let's see, I already mentioned that in the box you get this meter, you get a 9-volt battery, and you also get this short set of test leads. That's the other thing that comes with it, and those plug into these banana connectors. Ignore the guard one, that's rarely used. And then that allows you to clip onto components that you can't easily connect using the integral connectors here. The meter also comes with a fairly thick printed manual, which looks really impressive until you realize it's printed in about 20 zillion languages, and the part that's in English, or pick your favorite language, is only a few pages long, and you get very perfunctory descriptions of the features without a lot of explanation. So it's not really that great of a manual. At least it tells you what the buttons do, but it doesn't explain very well how to use them. There may be more information on the website. I haven't looked. And by the way, I did mention the user's manual. This is the user's manual here again. It looks pretty impressive. It's kind of thick. You think, boy, there's a lot of good information in there. It gives you a quick list of features, a brief description of what each button and part of the display does. Well, not part of the display, there's a single description for the entire display. And then there's a basic operation, how to set it up, how to turn it on, how to manually change the ranges and the secondary parameters, the series or parallel connections for testing, the frequency button, the data hold, the relative/percent function, which allows for percent deviation measurements from a stored reference value, which you can program into the meter, and sorting. The sorting mode is used to select components within a percent limit of a reference value. And the percentages you can key in are 0.25, 0.5, 1%, 2%, 5%, 10%, 20%, and all those are plus or minus values, and then a plus 80, minus 20. So it doesn't really give you a whole lot of information to go on there. Then it talks about the calibration and its open and short parts of the calibration process. Backlighting, how to use the guard terminal, auto power off. Powers off after 5 minutes of inactivity. The meter will alarm or beep 3 times before the power is shut off, and I have seen that work. Pushing any button will reset that and continue using the meter without the auto shut off. The RS-232 output port is not active on this meter according to this. And it mentions if you want to use the AC adapter, meaning any regulated DC power source of 9 volts and at least 1 amp, it's sort of on you. You have to get it from a third party. Talks about the battery indicator and replacement of the batteries, and it mentions the 2 accessories which are available. And then it goes into the specifications, electrical specifications, DC resistance, AC resistance, capacitance, and inductance ranges. Let's see. Does it actually tell you what the minimum and maximum readings are? It does not. Now, he gives you these specifications and it barely describes what it's talking about. Apparently it's relating only to the accuracy. So it doesn't give you the range. I don't see where the range is mentioned anywhere on here. And apparently Extech is owned by FLIR or FLIR Systems. They're the ones who are warranting it. Even though this is a fairly new product, about 6 years old, according to this date here. And it has a, I don't know if the support phone numbers even work anymore. I tried the support email address that's in here, and it got a bounce back saying it wasn't valid anymore, and it directed me to the Extech website through a FLIR website, and I just got to their support portal, which is what I use to try to contact them. Anyway, so that gets up to page 11, and considering 3 more pages are used for specifications, you're only going up through page 7. Starting with page 2, which is 6 pages of actual operator's manual, and after that you're in all the other languages, German and Spanish and French and what have you. So again, not a great manual, probably enough to get you going. It may not be adequate for the more esoteric functions like the sorting features. It seems kind of sketchy for that. So I'm turning on the meter here, and it flashes the display, and then it goes into its self-test, and now it's saying overload, which just means there's no component plugged in at the moment. I'm going to plug in the minus test lead and the plus test lead. And the reason I'm doing this right now is because, at least on this particular meter, I found these connectors here to be almost unusable. The spring force is so strong between the plates that I found it very difficult to get component leads to actually go in there. I've contacted Extech about this. I haven't heard back from them yet. I don't know if they have a fix or not. Maybe this is a fluke, but I sort of doubt it. I think they've screwed up on this. That's my personal guess here. It seems very unlikely that this would be the only one that has that problem. And it's a pretty new product, is my understanding. So I don't know if other people have had a similar complaint. I've been looking all over the internet for other reviews, and there's only a couple of reviews, and they don't mention the connectors at all. So, and actually the only one review I did see, they were just using these right off the bat without explaining why they were doing it that way. Anyway, when I try to plug any component lead in here, the leads just bend rather than go in between the springy contacts. So I'm going to have to do that here. As with most of these LCR and LC meters, they have some input protection, but they can be damaged by plugging in a capacitor that has a substantial charge on it. So they always have a caution on there to discharge components, and that would not really apply to inductors, but it would apply to capacitors. You want to touch the leads together to short them out and remove any residual charge before you go plugging them into the meter. So this is ostensibly a 470 microfarad electrolytic capacitor. It has auto-ranged, and it's figured out that it's a 422 microfarad component. It's defaulted to 100 kilohertz, and it's giving me a bar graph here to 100%. and I don't know what that is supposed to be. Percent of what? It's not reading out anything related to 422, and it's not relating to the other secondary value is currently the D, or the dissipation. I haven't figured out what that bar graph is for yet. Anyway, so it's defaulted to 1 kilohertz. Let me turn on the backlight, it'll be easier to read. A little less glare. So it's defaulted to 1 kilohertz, which is maybe a little higher than you would ideally like to have for a sizable electrolytic capacitor. So I'm going to change the test frequency. It's going to go up, and here it can't even give me a decent reading at 10 kilohertz, and the same will be true for 100 kilohertz. Now it rolls over to 100 hertz, and it's going to give me a 444 microfarad reading here. And if I go up to 120 hertz, the value goes to 442, so it's dropped slightly. If I go back to 1 kilohertz, it's gone down to about 420. So I'm getting around 444, 442, and then the value drops substantially once I get to 1 kilohertz. So let's say it's 444 thereabouts. I'm going to disconnect the test leads. I'm going to short the leads together. I'm going to spread the leads again, and I'm going to try my old Heathkit 2240 here, put it on its 2000 microfarad range, and plug in to the Kelvin connectors on the front, and it reads 443, which is almost an exact match. I have done quite a bit of testing so far on this Extech meter, and in the past the only way I had to set this up was either by the primary calibration method of adjusting it to some reference inductors and capacitors, or to use methods of frequency counters and things like that. I've tried both methods, I get about the same results. I have access to a lab that has a professional LCR meter, and I get some low leakage, high reliability, high stability parts in several different sizes of capacitor, and I go in there every few years and ingratiate myself with the people at the lab, and they let me borrow their meter to take new readings on those test components, and then I bring them back and touch up this meter, and I almost never need to really adjust it. It's been very stable. But the fact that this meter here so closely matches what this meter is doing is well, it makes me feel more confident about both of them, really. So let's reconnect this capacitor. So I've reconnected the capacitor to the Extech. I'm back to 120 hertz, and by the way, the Heathkit 2240, I don't recall off the top of my head, but I seem to recall that it has more than one test frequency as well. It may only have a couple. I doubt it has 5, but I think it does have some test frequency adjustment depending on which range has been selected. Whereas this is auto-ranging here, but it doesn't auto-range the test frequency. So anyway, I'm connected here, and I really wanted to just go over and look at the secondary display here. So right now it's on dissipation, which is 0.049, and maybe I should go back and test it. 0.049, and the backlight just timed out. The Heathkit meter does have a dissipation feature. I've never used it. I don't know what I'm going to get here. Okay, well, it's giving me a different value, but it's not in some totally different range. It's 0.088, so it's different from what the Extech is telling me, but it's sort of in the ballpark. I've reconnected the capacitor to the Extech, and you can see here that the dissipation is now 0.16, so it's roughly twice what the Heathkit said. And if I cycle through the frequencies back to 100 Hertz, the dissipation is 0.046. At 120 Hertz, it's 0.048. At 1 kilohertz, it jumps to 0.169. So somewhere in there is the 0.088 that the Heathkit came up with, and it's clearly dependent on frequency. So the two meters might actually be agreeing with each other, but it may be that the frequency that the Heathkit is using is somewhere between 120 Hertz and 1 kilohertz, and that would account for the difference in dissipations. Now pushing this button by itself doesn't seem to change it. The manual says I have to select the primary display first. So I'm going to push that, and right now it's millihenries, and there's capacitance, manually selected. Now will it let me select this? Yes, it does. So that's sort of odd. If you're going to take it away from its defaults, you have to first specify the type of component, and then you can do this. So now I've switched it to Q, 18.58. The equivalent series resistance is only 0.1 ohms. The theta is minus 86.8, and that's related to the phase shift between current and voltage through the or on the part. And then we're back to the dissipation again. So I'm going to try this on a couple other component values now. This is a 100 microfarad ostensibly part, coming in at about 89 microfarads. And plugging it into the Heathkit, about 89 microfarads again, very slightly different but pretty much the same value. Here's a 3.3 microfarad part, and it's coming in at about 3.2. Let me try changing the frequency. So 3.2 at 100 Hertz, 3.2 at 120 Hertz. So I'm going to go with 3.2. And plugging it into the Heathkit, right in the same ballpark. Now I'm going to go to some smaller value disc capacitors, little ceramic capacitors. Now for these I'm going to try to use these flat connectors, but it's going to take some work to and here's what I've been reduced to trying, is using a needle nose pliers to get in pretty close and try to protect the leads. Line it right up with the connectors and try pushing it in there. But all it does is it bends the lead around. It just doesn't want to go in there. Luckily I use this so infrequently that I can probably live with that, but it really sucks. So I have to go back to these test leads again. So this part is now connected this way, and I'm going and running it at 120 Hertz. I'm thinking that, let's see what it does at different frequencies. So it's reading about that there, 1055, 1028, that's 10 kilohertz, 992 at 100 kilohertz, and so the value is a little high there. It goes progressively closer to where I expect it to be. Up around 10 kilohertz, it's reading in at 1026.9 picofarads, which is basically 0.001 microfarads. 0.001 and then some change. So on the Heathkit it's giving me again about 1 nanofarad, which again is about 0.001 microfarads. And I actually do have this other multimeter which is supposed to be able to read low range capacitors. Well, I wasn't able to hold the test leads on the part while reading it, but it read a little bit high, but then I didn't have the components in isolation. I had them down against a piece of paper, and my hands were practically on the test leads, which would have added some parallel capacitance, so it was going to read a little high, but it read about 1.4 nanofarads, or 1.4 nanofarads, so it's a little high, but taking into account some parallel capacitance from just the way I was testing it, it's probably not too far out. So that seems to be about as expected. Now this guy here should be a 0.01 microfarad part. So 10 times what the other one was. It's reading at 10 kilohertz about 0.9. Let's cycle this. Or 9 nanofarads. It's staying pretty consistent regardless of which frequency I'm testing it at. Sticking in the mid-9s. So roughly 9 nanofarads. Heathkit's reading a little bit lower, but it's bouncing around a bit. It's actually sneaking up on it. Now it's stabilizing. I'm not really sure why it is creeping up on it like that. Now it seems to be slowing down, so it's sort of in the same ballpark. This guy here read 9.7, so again, very close to what the Extech was giving us. And this also creeps up on me. That may be a characteristic of the ceramic cap here. Some parasitic values that are changing, but 9 point something and it's creeping up on it. So they're pretty much in agreement. And finally this one here should be, I think, I think this one's 0.1. I may have stumbled over myself when I was talking about this previous capacitor at 9 nanofarads. That's the same as 0.01 microfarads. I may have said 0.001 or something like that. But now the newest component I've got here should be a 0.1 microfarad part. Okay. And it's creeping up on some value. That's at 10 kilohertz. So it's still rising. Gonna see if it stabilizes on something here. And these are really old parts too. These have been in my bin for decades. I'm not going to try to get into the reasons why it's doing this. Pretty high series resistance. Seems to have slowed down. Let's just call it 86 nanofarads, just because I'm tired of waiting. And the Heathkit's starting out there low too, but it's rising. It's slowing down around 83, but it's going to go higher. Not much change at this point. Let's just say 84 versus the 86 the Extech gave us. And then I'm going to put my test leads from the third meter on this. And although you can't see the meter, it's rising just like the other one did. It's passing 86, it's still going up. And it looks like it's stabilizing maybe at 91 or so nanofarads. So you can definitely get different results with differences in the meter circuitry, how exactly it's doing the testing. There's different methods of testing capacitance values, and it also is going to depend somewhat on the frequency used and some other factors. But these are not high precision parts. You usually don't care when you put these in a circuit, these small value capacitors, if they're exactly one value or another. If you're within 20%, you're lucky. So the fact that these three different meters are coming up with numbers that are pretty close to each other is a good indication. Anyway, I don't know that there's much else I can say about this. I'd be a lot happier with this if these connectors here worked. I'm going to be debating whether I want to return this if Extech doesn't have a good response to my complaint. You know, if they offer to swap it out with one, especially if they don't offer to replace the missing screw on the back. I could also return this to Amazon for another one and hope that that one's a little better, but I honestly don't know why the spring force on these would be any better. So it's sort of a conundrum. We'll have to see, but anyway, I hope that this quick overview and demonstration of the Extech LCR200 meter has been useful to you.